Alrighty everyone, today we are going to be doing our 3.2 notes. So if you've not already picked up the 3.2 notes from by the window, please go do that now and then turn to your table of contents for Unit 3. So these are going to be our 3.2 notes, and this is interpreting exponential functions. Remember, when we are interpreting something, we are telling the meaning of it in the context of the problem. So you are going to see word problems here, and we need to interpret what those functions mean in the context of the problem. So this is going to be for me on my notebook on page number 18. So I'm going to come back over to our notes. Our 3.2, interpreting exponential functions. We're still using the same the same learning target. I can use exponential functions to model real-world phenomena. And the fact that we are modeling real-world phenomena, this is why a really key reason on why we want to be able to interpret these exponential functions. Because when we're, a function by itself is all good and great, but what does that actually mean when we're looking at a function that models something real? So below you'll see a model for a half-life of a radioactive atom. So you see that it's exponential decay. We could definitely have an equation for this, but what would that equation mean for this radioactive atom? That's what we want to work on today. Go ahead and open those notes up. Coming back up here. So last in our 3.2 notes, we did write down our equation of our function. Let's see. So let's write that down again. We're just going to add one little piece here. So we have A times B to the x over n. So we just had x last time because a lot of times this n is just equal to 1, but we're going to talk about what that n means in a little bit. So the a, if you remember correctly, was our initial or starting value. That initial or starting value of our function. It is also the y-intercept of the graph, so when the x equals 0. So if you're looking at the graph of a function, that initial or starting value is when that x is 0, so that is our y-intercept. The b is also known as the base of our function, and when it's written as a decimal, we used that 1 plus the growth or decay rate, 1 plus r, to figure out what that growth or decay rate is. So remember that R was the growth or decay rate. So if that R was negative, we know we'd have decay, and if the R is positive, it is growth. Just to note, if for a percent increase or decrease, make sure we're using the decimal form. So if you're given something that says that something is increasing by 15%, we want to divide that by 100 to get its decimal form. So remember, 15% is 0.15 because we would divide it by 100. Now here I have x or t equals, because a lot of time in this, we are using time in context, so we want to, sometimes we'll use t, but remember that this is our the time period here, right? So how much time or how many x's are we looking at? And then the n, this new thing here, the n is the interval of time. Excuse me. The interval of time that something is increasing or decreasing by. So maybe something isn't increasing every single day. Maybe it's increasing every 3 days. This would be your, that 3 would be your interval of time. Let's look at a few examples here. You open a new savings account for college. The amount of money in your savings account can be modeled by the equation f of t equals 1,000 times 1.05 to the t power. I'm just going to box that equation. I also always like to put a box around it so I just identify what it is. My eyes can easily come back to it. Interpret each piece of the function in the context of the problem. Okay. So when I'm interpreting each piece here, I'm thinking about what is the A? What is the B? And with that B, what is the growth rate? Can we figure out what that is? And then what about this part up here? What does that mean? So that's what we're going to be looking at here. So starting with the A, that initial value. Well, in the context of this problem, the A is 1,000. And because this is the amount of money in your savings account, well, that just means you start with $1,000 in the savings account. Since that is our starting value. The B is 1.05. Now, based on our 3.1 notes, I know that that is exponential growth, but to figure out how much it's growing by, we are going to use that 1 plus r equals 1.05. Subtracting 1 from both sides, I would get that r equals 0.05, or multiplying by 100, 5%. So that means that your account increases by 5%. And then the T is, since I don't see it there, the T is being divided by 1, right? We don't see the division by 1, so I have T divided by 1. So T means that the, T divided by 1, rather, means that your account increases by 5% for each T. Now, it doesn't tell us what T represents. It's likely that it's years, since that's typically what we use for savings accounts, but we don't know that for sure since the problem doesn't tell us that. Let's take a look at another example. Example number 2. The population of a city in Iowa can be modeled by the equation P of T equals 1,860,000 times 0.98 to the T divided by 4, where P of T represents the population and T represents the years since 1900. Ooh, that was a very large city in 1900. Maybe this is just the whole population of Iowa. Who knows? Interpret each piece of the function in the context of the problem. So same thing we just did. Starting with our A, our initial value here, right? So the A is 1,860,000. So how would we interpret that? Well, I see that this says since 1900 here. So the population of this city in Iowa was 1,860,000 in the year 1900, since that's the starting year. Then I can look at this B, that is 0.98. So B is 0.98. I know that 0.98 is less than 1. So I know that this is going to be decay, but how much is it decaying by? So again, if I use my 1 plus R equals 0.98, subtracting 1 from both sides, R is negative 0.02. If I change that to a percent, that is 2%, negative 2%. We can say the population decreases by 2%. And then I have this t over 4. So what does that t over 4 mean? Well, I know that t represents the years since 1900, and that 4 is the interval of time. So n is 4, and that means every 4 years. That's what the interval of time means. So if I see t divided by 4, putting that together with the population decreasing, we could say the population decreases by 2% every 4 years. If we just add on to that sentence, there. So we know the population of the city in Iowa started at 1,860,000 in the year 1900 and has been decreasing by 2% every 4 years. One more example for us to look at, the spread of alpha-thytis. It's a newly found awesome illness. It just means you get to be really good at math, so no worries if you get it. The spread of alpha-thytis can be modeled by the equation A of t equals 3 times 2 to the t power, where A of t represents the number of people with alpha-thytis, and t represents the days. T represents days. I'm going to want that later. Interpret each piece of the function in the context of the problem. So again here, the 3, that's going to be our A. And if we're interpreting that, A is, since A of t represents the number of people with alpha-thytis, there were 3 people with alpha-thytis to start with. And then I see my B is 2. We can either just use the 2. We could use our 1 plus R to figure out the percent. But since it's a nice simple number like 2, we can also say the number of people with alpha-thytis doubles, right? Because it's being multiplied by 2, doubles. And then finally we have this t, right? So t has that invisible divided by 1, which means the n is 1. And n being 1, since t is representing the days, is every 1 day, or just every day. So the number of people with alpha-thytis doubles every day. So when you're asked to interpret each piece of the function in the context of the problem, these are essentially the 2 sentences we are going to be writing about. What is the initial value in the context of the problem, and then also what is happening? How is the function increasing or decreasing, and how often? So just those 2 sentences, putting together your A, and then your B and the interval of time. Go ahead and glue these notes into your notebook on that next page, and you can work on your next assignment in Mastery Pathways.